Hi guys, I have a challenge problem here with me today. So it's problem 3.47. If I'm a little bit out of it, just please excuse me. I've had a really long day today at work and some other things. So a test rocket starting from rest at point A is launched by accelerating it along a 200-meter incline at 1.90 meters per second squared. Figure P 3.47, which we have in the bottom right corner. The incline rises at 35 degrees above the horizontal, and at the instant the rocket leaves, the engine turns off, and the rocket is subject to gravity only, ignore air resistance. Find A, the maximum height above the ground that the rocket reaches, and B, the rocket's greatest horizontal range beyond point A. Okay. So because we already have this diagram, we don't need to draw anything, but let's just go over the information so we know everything that we have, and we can just get better acquainted with the information. So we have a 200-meter incline, which we have right over here. We have 1.9 meters per second squared. Well, we don't have that in the diagram, but we have this 35 degrees above the horizontal. And we have that right over here. That's 35 degrees above the horizontal. And we want to find out what the maximum height above the ground is that the rocket reaches. So when we do that, so now that we have that, we can go ahead and we can just write down all of our knowns. So let's start with the y component. So we can actually do two things in this situation. We have to remember that in this problem, we have two sort of different dynamics going on from bottom to top, right? On this ramp, we have separate information going on, and then we have different parameters as soon as we leave the ramp. So we can do x and y for the ramp, and then x and y once we leave the ramp. So we can just write that down right now. Okay, so for the ramp, we can do, we can write down our information given. So really, even though there is acceleration in this sort of strange incline, right? We know that this has both an x component and a y component, but we can just treat it as one-dimensional if we shift our coordinate system, right? So we're just going to say that this is positive and this is positive right over here. So as long as we say that those two are positive, we're just going to treat this like a one-dimensional problem. So we have distance is equal to 200 meters. And then we have acceleration, which is equal to 1.90 meters per second squared. And we know that if we're starting from rest, it's VI is equal to 0 meters per second. And we want to know what the maximum height is and what the greatest range is. Okay, so that's all the information that we've been given. We don't know how long this is going to take or what the final speed is, but sort of looking at this problem, our intuition is telling us that time isn't really valuable. What's really going to help us in this problem is VF. So now let's look at post-ramp, what happens. So now we can implement a new coordinate system. So once this rocket leaves the ramp, what we can do is define a new coordinate system. And we can just treat it as normal. We can say that this is x plus x, and this is plus y. So now let's write down everything that we know in the x and y direction. So for y post-ramp, we know that our VI is going to be equal to VF ramp sine 35, because we're still going to be at this angle, right? Once we leave, we're going to be at, so let's see, this is the ramp. as soon as we leave that instant, we're still going to be at an angle. So we just want our sine component. So we have VF ramp sine 35. We're going to have acceleration is equal to minus 9.8 meters per second squared. We're going to have, what else? We know that I guess we can say that the height that it's going to reach back to the ground, we can say that that is going to be the ramp rates. So if we have this ramp, it's going to go in this sort of motion, it's going to go back down. But the difference between this and this is just this height of the ramp. So we can say like dy ramp is equal to 200 sine 35. And we don't really know how long it's going to take or what this final speed is going to be. We don't know that. Or I can just say VF, and we can go ahead and label these as VF ramp. And this can be ramp as well. Okay, so I'm just going to go ahead and erase this. And then for X, for the X component post ramp, we can say X post ramp. We know that we know that for X in any projectile motion type of question, it's just going to be dx is equal to Vx times t. So what we need to do is we need to find out this time. And remember that this time right over here is going to be the same as this time right over here, because we can only travel so far in the horizontal component as long as we are in the air, right? So if something's in the air for 1 second, it's only traveling horizontally for 1 second and vertically for 1 second, right? There's no way that it would travel, it would only be in the air, this ball or this rock that's arching, or this rocket in this case, that's, going through this projectile arch in the air. It's going in the vertical component 5 seconds and 2 seconds in the horizontal component. That doesn't make any sense. So these both times are the same. And then for Vx, we know that Vx has to be V ramp, VF ramp, right? So as we're leaving this, it's going to be the X component of this speed, or the X component of this speed. So that's going to be cos 35. And that is, if we want to find out, t's we don't know. And then if we want to find out what dx is, we have our formula right over here. That's how we would find dx. And that's how we would find the greatest horizontal range beyond point A right over here. Okay, so one thing we can also say is, one thing we can do, actually, before we go ahead and write down any more notes, we can just go ahead and start with the question. So if we have part A, we want the maximum height above the ground that the rocket reaches, right? So if we're starting at some sort of V, I don't know, doesn't matter where it is. What we know is the way projectile motion works is that it's when it's doing some sort of when it's doing some sort of when it's going through the y component of motion, it goes up, and then as it's deaccelerating because of gravity, it, for a split second in the air, like less than a split second, it stops and then it changes direction. So what we know is that VF top is equal to 0 meters per second. That's what we know, because that's just a property of projectile motion. Okay, so because we know that, and we're trying to solve for the maximum height, we want to find out what height is, right? So we don't know that. And then what other pieces of information do we know? Well, we're trying to find out the maximum height above the ground that the rocket reaches. So this problem's a little bit tricky, but we can use our y post ramp, right? Because once it's off the ramp, that's actually when the engines turn off. So that's actually going to be the part where only gravity is working on it, and it's going to deaccelerate and reach that, 0 meters per second, and then we're going to move back down. But sorry, before we get ahead of ourselves, we are going to use the y post ramp, all the information that we have post ramp. So we know what our VI is. It's going to be VF ramp. But how do we get VF ramp, right? How do we get this information right over here? To get that, we need to solve for VF ramp. We have to solve for the final speed while it's still on the ramp. So to do that, we are going to use one of the 5 kinematic equations, right? Because we have our 3 knowns here and we have our 1 unknown here. So let's go ahead and do that. We have, with this equation, we're going to have the VF is equal to VF squared is equal to VI squared plus 2AD. And when we plug in our values, right, we're just going to plug everything in. We get, we're getting 2 times 0 plus 2 times 1.9 times 200. And then we're going to square root that, right? We're going to get VF is equal to 27.568. So that's our VF. That's going to be 27.568. And this problem is a little bit tricky, but the reason why I like it is because it includes rockets. And I actually, just fun fact about myself is that I work in the space sector. I work in the space industry. I'm not going to go ahead and say exactly for which country I work for. Maybe I'll really reveal that one day, but we're getting off of topic. So back to our question. We have our VF ramp. So right as it leaves the ramp, it has 27, the speed is 27.568 meters per second. Okay, great. So that means we can use that information right over here. So right when we're starting off the end of this ramp, we leave at some speed. We have this acceleration due to gravity because we no longer have this 1.9 anymore because the engine's turned off. And what other information do we have? Oh yeah, we have this piece of information, VF top. So we have our 3 knowns. We have and we're trying to find our H. So we have our VF top, we have our VI post ramp. So we're just going to say VI is equal to 27.568 sine 35. And then we have our acceleration, which is minus 9.8 meters per second squared. And when we do that, this is D. So which equation do we use? We are going to, again, use the kinematic equations. So we have, again, VF squared is equal to VI squared plus 2AD. And what we get is, this is going to be minus 15.824 squared, right? So this is actually squared, and we move it on to this side. We subtract VI squared from both sides, is equal to 2AD, which is 2 times minus 9.8 times this distance, which is the height that we don't know. Anyways, when I plug that in and I solve for that, what I get is D is equal to 12.7568 meters. And I'm just going to double check that on my calculator because there's so many steps here. I just want to make sure that I'm giving you all the correct information. Okay, yeah, that looks about right. I just did it again and I have the same numbers. I think I might be off by a few decimal places, but that's probably just a rounding thing. Okay, so let's take a look at the question again. The maximum height above the ground that the rocket reaches. So remember that right now we just solved for this height. So we did starting from here all the way down till here. So this is sort of like the building problems, right? So we're ignoring this and we're saying that this is the height above the ground that we just solved for. That's 12.7568. But this ramp also, how do we find this height, the height of the ramp? And we should have that right over here, like we said. It's going to be 200 sine 35. So our actual height, and sorry, I'm just going to erase this part right over here. So our height for part A is equal to 12.7568 plus this 200 sine 35. And from that, I get 163.83 meters. Oh, so sorry. No, that's not what I get. That's not what I get. Sorry. Just going to plug that into my calculator again. I have so many, my notes are a little bit messy today, so just bear with me. I have 127. I have 127.49 meters. That's my height above the ground, above, this point all the way to the top. So that's find the maximum height above the ground that the rocket reaches. It reaches 127 meters above the ground. And of course, if you're doing this question and I'm off by, we can see that this is 0.49. So really, if you get 0.51 and you round to 128, that should be fine. But it should be, reasonably within some sort of, it should be reasonably around 127.49. Okay, so there we have it for part A. Okay, so now for part B. So I'm just going to write down A right over here is equal to 127.49 meters. And I'm just going to go ahead and erase all of this. So now the second part of this question, we're looking for the horizontal range. So the horizontal range beyond point A. So this is actually similar to the question in part A, because in part A, we solved for this distance above, and then we had to solve this y distance from the ramp as well. But in this question, so sorry, not but like similarly in this question, we're gonna have to solve for this portion and this portion. I'm just gonna do that in a different color so it's a little bit more intuitive, but we're gonna do this portion and this portion. But because there's two different accelerations going on, we have to solve them separately. So we can actually go ahead and do the ramp first, just because I think it's like so much easier. So I have yellow there too. So I'm gonna actually solve this in blue. But if we want to find out, just to get this easy part out of the way, so the x distance by ramp. The x distance by ramp is going to be 200 cos 35. That's going to be the x distance by the ramp. Now, this other component right over here is what we're going to solve for. So we have our vi, we have our acceleration. We also have our y distance that's going to travel, right? Because it's going to go down this distance right over here. And what we want to find is t, right? Because once we have t, we can plug that into this equation right over here, and then we'll have the x distance that we traveled. Okay. So the kinematic equation that we're going to use is going to be the one that we typically use, the one that looks a little bit like this. So it's going to be d is equal to vi t plus half of at squared. Okay, so we know that this d ramp is actually going to be in the minus direction. So it's going to be minus 200 sine 35. And the reason is because, well, we're starting off with vi, which is up, right? So we said that this is our positive y, which is up. So because we're traveling this downwards distance, it's going to be minus 200 sine 35. And that's going to be equal to VI, which is going to be this 27.568 sine 35 t plus half of minus 9.8, which is our acceleration, t squared. And then our t, I'm just going to give the answer. You can use, the quadratic formula. You can use an online calculator, but just for sake of time, this t that I'm getting, so we have two answers to t. So one is going to be minus 3.4872, and the other one is going to be 6.7137 seconds. So both are in seconds. And now that, because we can't have a minus time, it has to be the positive answer. So dx is going to be, so we plug in our VF ramp. So dx is going to be equal to 27.568 cos 35 times 6.7137, and then we get our dx. And in this case, the dx that I'm getting, I'm just going to plug this into my calculator because I have so many numbers on my page. So I'm getting that it's 151.5978 meters. Okay, perfect. And this 200 cos 35 is 163.83 meters. So now, because we want this distance range beyond A, we have to add these both together. And when we do that, what we get is 315.43 meters. So that's our range. That's our answer for part B. I hope this was helpful. This was a challenge problem, so feel free to go back and just watch some parts a couple of times if you don't understand them. If you have any questions, please feel free to send me an email or leave a comment below in the video, and I'll get back to it as soon as I can. I am quite busy with school and work, so I will, as soon as possible, I'll get back to you. Thank you so much for watching. And if this was helpful, please don't forget to like and subscribe. It really helps me get to know, especially when you like a video, it helps me know like what type of content to create for the future, because sometimes I'm just like, I don't know which problems to do. So liking my videos that, you like, or you want to see more similar content to, it helps me know like what type of problems to do in the future. So thank you so much for watching again, and see you next time.